In this video, I want us to talk about acids and bases. So we have two theories that we're going to base our definitions on. The Arrhenius theory and the Lorentz-Bronsted theory. So under Arrhenius theory, an acid is a substance that produces hydrogen ions, while a base is a substance that produces hydroxide ions. But that's very vague. Let's go ahead and take a look at how that actually looks like. So, Arrhenius theory. An acid produces hydrogen ions. Let me show you what I'm talking about. So, for instance, let's take HCl as an example, and then plus H2O. What are we going to get? We're going to get Cl minus plus H3O plus. This presence of H3O plus is what we refer to as hydronium ions. But the definition says hydrogen ions. So why are we now talking about hydronium ions? Well, they, for the most part, treated the same. Take a look at this. HCl can give us H plus plus Cl minus. So if a substance produces H3O plus or H plus, then it is considered an acid. It produces hydrogen ions or hydronium ions. So this is how we define an acid under Arrhenius theory. Let's go ahead and take a look at a base once more. So we said that a base is a substance that produces hydroxide ions or OH minus when it dissolves in water. So let's go ahead and take a look at that. So which base can we use? Let's take NaOH. We're going to come across this base so many times. It is sodium hydroxide. So NaOH, let's dissolve it in water. What are we going to get? We're going to get Na plus OH minus. This is a base. When dissolved in water, it produces hydroxide ions. Do you understand what is going on?
Not really, especially on acids.
Okay, what is the issue there with the acids?
Okay, so it was said that HCl plus H2O give us H3O plus Cl minus, right?
Yeah.
So here he said HCl gives us H plus Cl minus. Does it mean that the H plus that HCl gives is dative covalently bonded to H2O?
Oh, yes. Yeah, that is grade 11 knowledge right there, covalent bond. I forget about that sometimes. Yeah, I think we can say that. We can even go ahead and draw a low structure diagram and see if we're gonna get H3O plus. But I know this to be true. It's just that in grade 12 physical sciences, we don't even think about it. We just know that HCl plus H2O will give you Cl minus plus H3O plus. So these two equations, they're gonna lead to the same consequence all the time. So whether in an exam you decide to use this equation 1 or you decide to use this equation 2, the consequences are going to be the same. That is going to be clearly demonstrated when we solve some problems. Can you take a look at the second definitions? Okay, Lorentz-Bronsted theory. This is actually the easier between the two. Arrhenius theory, well, it's still easy, but Lorentz-Bronsted theory is relatively easy compared to Arrhenius theory. So what does Lorentz-Bronsted theory say? Let's take a look. An acid is a proton donor and a base is a proton acceptor. That's it. That's the definition. You can come across this in the exam for 2 marks. What is an acid? And then you say proton donor and then you get 2 marks. So 1 word, 1 mark. And then a base is a proton acceptor. Alright. And then obviously, if you talk about the acceptance of a proton and the donation of a proton, then we go ahead and talk about what we refer to as an conjugate acid-base pair. We talk about what we refer to as a conjugate acid-base pair. Okay, but before we can just talk about acid conjugate base pairs, let me just show you what we're talking about when we say that an acid is a proton donor and a base is a proton acceptor. Maybe before we can do that, tell me, is H2O an acid or a base?
It is a neutral substance.
Okay, right. Most of the time, if it is reacting with an acid, it is going to act as a base, and then if it is reacting with the base, it's going to act as an acid. And we can show this idea of an acid being a proton donor and a base being a proton acceptor clearly using a reaction between an acid and a H2O, a reaction between a base and H2O, and even just a reaction between a common acid and a base. We can still demonstrate that fully well. So let me show you what I'm talking about here. Let's say, for instance, we have HCl plus H2O. There we go again, to give us Cl minus plus H3O plus. Okay, so take a look at this definition. An acid is a proton donor. What do we mean by proton donor in our case? H plus. And the base is a proton acceptor, H plus. So take a look at HCl. We start with HCl, and then now we have Cl minus. So what has happened there? From HCl to Cl minus, what has happened there? Well, we had a proton, we had H plus, and now it's no longer there anymore. It would imply that this HCl is an acid because it is a proton donor. It has donated a proton. It was HCl, now it is HCl, it is Cl minus. Initially it was HCl, now it is Cl minus. So clearly it has donated a proton. So we would refer to it as an acid.
Okay, does it mean that to classify a species as an acid or a base, we do not consider the hydrogen?
You'd have to explain to me what you mean by that when you say we don't consider the hydrogen. In this example that we have, what is leading you to say we don't consider a hydrogen when we consider a species an acid or a base?
Okay, it is because to consider HCl an acid, we spoke about Cl being negative, and we did not talk about H being positive.
Okay, our definition is that an acid is a proton donor. So the only reason why we're saying that HCl is an acid is because it has donated a proton. Because take a look at this. HCl is made up of H plus and Cl minus. So this is HCl, right? And then after it reacts with H2O, we now have Cl minus plus H3O plus. So it has donated a proton. That's why we're referring to it as an acid.
Okay.
Okay, so let's get rid of this. So HCl in this case is our acid. Okay, and then if this is an acid, then the H2O will act as a base. But is it clear that it's a base without putting that into context? What is a base? A base is a proton acceptor. So tell me, does H2O accept a proton?
Yes.
Yeah, it accepts a proton to become H3O plus. So because it accepts a proton, we refer to it as a base. That's it. That is Lord Bronsted theory. So HCl is an acid because it donates a proton, and H2O in this case will be a base because it accepts a proton. Right. So that is acid, that is base. We're about to talk about conjugate base pairs in a few, but let me just give you another example of a reaction between an acid and a base. Right, so instead of using H2O, let's just go ahead and use NH3 plus H2O. So NH3 is a common base, and H2O in this case will act as an acid. But what are we going to have ultimately? We're going to have NH4 plus OH minus. So let's go ahead and break these down. Take a look at NH3. Is NH3 acting as an acid or a base in this situation?
it is acting as a base.
Why do you say that it is acting as a base?
That is because here it accepted a proton.
And then H2O on the other end?
It is acting as an acid.
And why is that so?
Because if we have a base here, H2O will act as an acid, and it has also donated a proton.
Right. Okay, so we say that this is a base because it accepts a proton, and then this is an acid because it donates a proton. Right. Okay, so if this reaction was reversible, so we're taking a look at it from the product side going to the reactants. What would you classify OH as?
I would classify it as a base because according to Arrhenius' theory, it says that bases are substance which produces hydroxide ions.
Okay, right. That is according to Arrhenius' theory. If you were to classify it as a base and have to explain according to Laurie-Bronsted theory, what would you say in that case?
I would say that OH negative, OH minus is a base, and that is because according to Bronsted-Lowry, a base is a proton acceptor. Ooh.
Yeah, that's true. Yeah.
Clearly, we have OH minus, which has become H2O, meaning that it has accepted a proton, and NH4 will become NH3, losing a proton.
Okay, so OH minus is our base, and NH4 is what?
It's an acid.
When we break down a reaction in this way, this is what we refer to as an acid-base conjugate pair. This is an acid-base conjugate pair. Right, so if a question says identify a conjugate acid-base pair in the reaction above or in the reaction below, this is what you need to do. By definition, an acid-base pair consists of two species in an acid-base reaction. One acid and one base that differ by the loss of or a gain of proton. Right, so the difference between these base, let me change my color here. The difference between these base and this acid is a loss of a proton or a gain of a proton, depending on how you look at it. And then the difference between H2O and OH minus, still the same, is a loss or a gain of a proton, depending on how you look at it. So this is an acid-base conjugate pair. Right, so we've touched on the Arrhenius theory, we've touched on Laurie-Bronsted theory, and we've touched on conjugate acid-base pairs. Now let's take a look at an amphiprotic species. So it is a species that can act as either an acid or a base. A species that can act as either an acid or a base. A good example of an amphiprotic species, we used to call it an ampholyte back in the days, is H2O. Clearly, you've seen that when H2O reacts with a base, it acts as an acid. And then when it reacts with an acid, it acts as a base. So it is amphiprotic because of that. It can act as either an acid or a base. H2O is not the only species that can act as either an acid or a base. We'll see that as we progress. We're going to come across examples where we have an amphiprotic species, or we're supposed to identify an ampholyte, and it's not H2O. So for the time being, just remember that an amphiprotic species is a species that can act as either an acid or a base. But anyway, storage, let's go ahead and take a look at the following concept. Different acids and different bases have different strength and so on. That is our next aspect. That is what I want us to touch on. So we will talk about strength of weak and strong acids, dilute and concentrated solutions, and the Ka and the Kb values. Ka and Kb values derived from Kc, right? Chemical equilibrium. and then acid-base reactions and neutralization reactions. Right, so let's go ahead and take a look at it. A weak acid or base is one where only a small percentage of molecules will dissociate to form ions in a solution. A weak acid or a base is one where a small percentage of molecules will dissociate to form ions in a solution. Right, so weak acids ionize incompletely in water to form a low concentration of H3O+, while weak bases dissociate or ionize incompletely to form a low concentration of OH-. So if a base or an acid produces a low concentration of H3O+ or OH-, then it is considered weak. An example of a weak acid is hydrofluoric acid, HF, of which when it ionizes, it produces a low concentration of H3O+. We can see that denoted by the arrow here, that in the forward reaction, not much products are formed. Right, it produces a low concentration of H3O+. An example of a weak base is magnesium hydroxide, which only dissociates partially into Mg2+ and OH ions. Let's talk about this Ka value and Kb value that is derived from chemical equilibrium. So Ka will always take the products if they are aqueous or gases, no liquids or solids. So Ka in this case will be H3O+, and then multiplied by the concentration of F-, everything divided by the concentration of HF. Obviously, we're not going to include H2O because it is a liquid. In these expressions, we only consider gases and aqueous solutions. So let's take a look. Ka. So we're saying that this is a weak acid. So the Ka value, we expect it to be less than 1 in weak acids. So in weak acids, the Ka value is less than 1. For HCl, for instance, which we know to be a strong acid, the Ka value would be greater than 1. Why will the Ka value be greater than 1? Because our denominator will be greater than our numerator because it produces a higher concentration of H3O+, right? Here we have Ka being less than 1 because it is a weak acid. We're gonna have a proper fraction. If we have a proper fraction, it is a weak acid. But then if we have an improper fraction, then it is a strong acid. Our Ka value will be greater than 1. So this is for strong acids, right? And then we can also derive almost the same for bases. We have what we call the Kb value for bases. So it is the ionization or dissociation constant, of which still the same thing applies. If Kb is less than 1, then we have a weak base. And then if Kb is greater than 1, then we have a strong base, not a weak, but a strong base. We have a strong base, right? And then whether it is greater than 1 or less than 1, it is going to be decided by the concentration of OH-, right? So this is weak and strong bases. If you have a strong acid and you want to use it, most of the time you have to dilute it first just to weaken it a bit because it is too corrosive to use in its original state. So let's touch on diluted and concentrated. It is clearly depicted in this picture. Take a look at concentrated and take a look at dilute. When you take a look at dilute, you can see that we have a few molecules of whatever substance we have there, and then in concentrated, well, it is concentrated. Let's take a look at the definitions. A concentrated solution is one where there is a high ratio of dissolved substance, right, solute to solvent. And then dilute solution is one where there is a low ratio of dissolved substance to solvent, right? So that is concentrated and dilute. This is what we are essentially saying. An acid is strong if there is a high percentage of ions formed in the solution. And a base is strong if there is a high percentage of ions in the solution. An acid is going to be H plus and the base is going to be OH minus. And then a weak acid, only a small percentage of ions are formed in the solution, while a weak base is the same, right? Just different ions. In acid, we know that it is H plus, and then in bases, it is OH minus. Now let's talk about concentrated and dilute. Concentrated, large number of molecules of acid in a solution, while dilute, we have a small number of molecules in a solution. And then the base, well, quite the same, large number of molecules in a base solution, and then a small number of molecules of base in the solution, that is dilute. So we have talked about the strength, and we've talked about concentrated and dilute. What we're about to touch on now is what acids and bases is all about. You'll come across a question in the exam, 8 marks, 9 marks, in some cases even 10 marks, requiring all the things we are about to talk about now. So when an acid and a base react, they form a salt. There's something cool that we're going to talk about with regards to that. If the base contains hydroxide ions, then water will also be formed. The word salt is just a general term which applies to the products of all acids and base reactions. A salt is a product that is made up of the cation from a base and an anion from an acid. Cation, just positive ion, and anion is a negative ion. Right. A salt is a neutral ionic compound composed of cations and anions. It is the result of acid-base neutralization reaction. Right, so we know that when you have an acid and a base, one of the products that you're going to have is salt, right? Stories. And then when an equivalent amount of acid and base react, so that neither the acid nor the base are in excess, the reaction is said to have reached the equivalence point. At this point, neutralization has been achieved. So if we have equal amounts of acids and base, and then they react completely, and there's no base or acid in excess, we say that we have reached a equivalent point, right? And then that is where we can say neutralization has been achieved, right? Just to touch on this, if you have ulcers, your stomach produces too much acid, and the medication you take is just a base that goes and neutralizes that acid, and then you're just left with salt in your stomach and not the acid anymore. So these acid-base reactions, they're very key to a lot of medication that you take, to a lot of household uses. Right. And then equivalence point, let's take a look at the technical definition. When a stoichiometrically equivalent number of moles of both reactants has been added to the reaction. If the base contains hydroxide ions, then water will also be formed. Right? You've seen from the reactions we have covered up to so far that most of the time water is one of the products, or is one of the reactants. And there is something profound about H2O that I want us to take a look at. Take a look at this reaction between H2O and H2O. We literally have H2O plus H2O. So what's going to happen? One H2O will act as an acid and the other one will act as a base. And then consequently, we have H3O plus and OH minus. Right. H2O plus H2O to give us H3O plus OH minus. This is what we call autoprotolysis. It's the transfer of a proton between two of the same molecules. Right, we have a transfer of a proton here between H2 and H2O essentially. But what is the consequence of this? It leads us to the autoionization of water. Well, this is what we're talking about here. It's the reaction of water with itself to form H3O plus ions and OH minus ions. What is the equilibrium constant for the autoionization of water, or what we refer to as Kw? Well, clearly you can see that it is equals to H3O plus multiplied by OH minus, right? These are our products. And then for the reactants, we're not going to have anything because we have H2O and H2O, which are in liquid phase. And like I've said, we only consider aqueous solutions and gases, right? There's quite a difference between liquid and aqueous, which a lot of people don't realize, right? So H3O plus multiplied by OH minus, this gives us 1 times 10 to the minus 14, right? This is the equilibrium constant for the auto ionization of water. This right here is very consequential. We're going to use this time after time. We are going to derive a lot of things from this concept. H3O plus multiplied by OH minus, it's 1 times 10 to the power minus 14. Well, from this we can actually get to showing that pH is equals to 14. From this is where a lot of things stem from, right? You'll see that in a few, but for the time being, let's take a look at how we can use that to calculate ion concentration, right? Although you normally ignore the auto ionization of water in calculating the H3O plus concentration in a solution of the strong acid, the auto ionization equilibrium still exists, and it is responsible for a small concentration of OH minus ion, right? Let's take a look at example. Calculate the concentration on OH minus ion in 0.1 mole per decimeter cube. Well, you can see that this question doesn't make much sense. I think there's a typing error here. So let's take a look at example 2 instead. The concentration of a solution of NaOH, a strong base, is 0.01 mole per decimeter cube. Calculate the OH minus and H3O plus concentration in this reaction. Okay, let's go ahead and take a look at that. So we have NaOH, and we're supposed to calculate the concentration of OH minus and H3O plus. So how can we possibly do that? We know that NaOH associates or dissociates to form Na plus OH minus. We know this to be true, right? So NaOH minus and OH minus, well, they are in the same, they have the same volume, right? Because we are getting this OH minus from the NaOH, right? They're not reacting with anything else that would increase or decrease the volume. Even if that was the case, they would still be in the same container, so to say. So the volume would be the same. So the volume is the same, right? Is the number of moles, are the number of moles going to be the same? Well, the balancing coefficient of NaOH and OH minus is 1. So the number of moles are going to be the same also, right? So the volume is the same, the number of moles are the same, right? So are the concentrations going to be the same? Yes, they should be, because concentration is just number of moles divided by the volume. So what is the concentration of NaOH? The concentration of NaOH is 0.01 moles per decimeter cube. So the concentration of OH minus should also be equals to 0.01 moles per decimeter cube, right? So we have the concentration of OH minus, but using this concentration of OH minus, can we find the concentration of H3O plus using the concentration of OH minus? Yes, we can, using the auto ionization of water. That's why I was saying that that concept is very consequential in what we are going to be doing. Take a look at this. So OH minus multiplied by H3O plus, we had said that this is equals to 1 times 10 to the minus 14. Well, should be easy to see what we are going to do here. The concentration of H3O plus is going to be equals to 1 times 10 to the minus 14 divided by the concentration of OH minus, which is 0.01. Well, do I need to put that in my calculator, or I can just do it in my head? I think I can. So H3O plus is going to be equals to, let's take a look, 1 times 10 to the minus 12 moles per decimeter cube. Well, let me just verify that. So we have 1 times 10 to the minus 14 divided by 0.01. Right, I think we are good to go. So that is how you can calculate the concentration of H3O plus if you have the concentration of OH minus. This is not something that is optional. You are going to use this at some point of time. There is no way you're not going to use it. So yeah, it is better if you familiarize yourself with this concept. So right, I've said that the autoionization of water is what leads to the pH value, well, the max on the pH scale being 14. So let's go ahead and take a look at pH scale. Right. A secondary way of expressing hydrogen ion concentration, avoiding using very small number of exponential notation, is the pH scale. So right, the pH scale is just there to express the concentration of hydronium ion without using smaller number. Right, pH is used to measure the concentration of H plus and therefore whether a substance is acidic or basic. Solutions with the pH less than 7 are acidic, while those with the pH greater than 7 are basic. The pH scale ranges from 0 to 14, and a pH of 7 is considered neutral. See the figure below. Well, there's no figure to see here, but yeah, that's the pH. We are ranging from 0 to 14. Less than 7, it's an acid, and greater than that is a base. Nothing new there. We've been talking about that since grade 9. pH is used to measure the concentration of H plus, but in such a way that doesn't include using very small numbers, right? So pH, the formula for pH is equals to minus log of H plus, right? You can see here that the only input we have is the concentration of H plus. So the only thing that is affecting the value of pH is H plus and nothing more. And then this log here is what ensures that we don't have very smaller numbers, because if we just said pH is equal to H plus, we would still have consistency, right? We would still have consistency. We wouldn't have any issue per se, but then we use log so that those small concentrations can be presented or represented in digestible numbers, right? We don't have to use 1 times 10 to the minus 12, because think about what 1 times 10 to the minus 12 means. It means 0.0000011 zeros until 1. That is very strenuous. So instead of doing that, we introduce log, right? And then we get numbers from 0 to 14, and that is easy to work with. So pH is equals to minus log of H plus. But pH is not the only thing that we talk about here. We also talk about pOH. So this is how we measure the concentration of OH minus therefore. So pOH, as you've guessed, will be minus log of OH minus. So this is pH and this is pOH. Remember that we said H plus multiplied by OH minus is equals to 1 times 10 to the minus 14. Okay, let's introduce log on both sides. I want to show you something very cool. So if we were to introduce log on both sides, we would have log of H plus multiplied by OH minus, right? We can, if what you do on the left, we must also do it on the right. So here we're going to have log of 1 times 10 to the minus 14, right? But log of A multiplied by B is equals to log of A plus log of B. That is a log law, right? So what are we saying? We're saying that we're going to have log of H plus log of OH minus. We have applied a log law there. And then log of A to the power B is equals to B log of A. So A, well, let me not use B. B in our case is minus 14. We're going to have minus 14 log of 10. Right. But we know that log of 10 is 1. So let's just replace this with 1. 1 times minus 14 is just going to give us minus 14. If we divide both sides by minus 1, we're going to get... If we divide both sides by minus 1, we're going to get minus log of H plus minus log of OH minus being equals to 14. But what is minus log of H plus? This is pH. And then minus log of OH minus, this is POH. And all of this is equals to 14. So there we go. pH plus POH is equals to 14. We are also going to use this concept at some point of time. Okay, let's solve some problems. Calculate the pH of a solution where the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube. So what is hydronium ions? Hydronium ions is H3O plus. And I've said that in place of H plus, we can always use OH, not OH, but H3O plus, right? So if you're given the concentration of H3O plus, you just treat it as H plus, right? So here we're supposed to calculate the pH. There isn't much to do. It's just direct substitution, really. So we're going to have pH being equals to minus log of H3O plus, right? We can use H3O plus and H plus interchangeably. This is going to be equals to minus log of 1 times 10 to the minus 3, right? So let me just go ahead and put that in my calculator. So minus log of 1 times 10 to the minus 3 is equals to 3. So the pH in this case would be equals to 3. If the concentration of hydronium ions is 1 times 10 to the minus 3 moles per decimeter cube. Well, the pH is equals to 3. It's easy to see that the POH should be equals to 11, because the pH and the POH, if you say pH plus POH, you get 14. So if pH is 3, then POH should be 11. We can easily prove that, but stories. I'm sure we're going to have a question where we're going to have to do that as time goes. Example 4. In a 162 centimeter cube solution of ethanoic acid, the following equilibrium is established. We are given an equation here, and then the question says the number of moles of CH3COO minus is found to be 0.001 moles. Calculate the pH of the solution.
So we've been given the number of moles of CH3COO minus, and it has been given as 0.001 mole. So the balancing coefficient of CH3COO minus is the same as the balancing coefficient of H3O plus. And the balancing coefficient of H3O plus is the same as that of ethanoic acid. So the number of moles of H3O plus and the number of moles of ethanoic acid is equal. We've been given the volume of the ethanoic acid as 162 centimeter cubed. But using the formula of C equals to N over V, the volume of ethanoic acid should be in decimeter cubed, not centimeter cube. To convert centimeter cube into decimeter cube, we will have to divide 162 by 1000, which will give us 0.162. Therefore, the volume of H3O plus will be 0.162 decimeter cubed. So to calculate the concentration of this H3O plus, we will have to divide the number of moles, which is 0,001, by the volume, which is 0,162. And that will give us 0,006. 0,006 moles per decimeter cubed. So the formula of pH is equals to negative log of H3O plus, which can also be H plus. pH will be equal to negative log of 0,006, which will give us 2,22.
It is as if every time we touch a different aspect, I keep on saying, oh, this is very important, we're going to use it at some point of time. And I just have to say it again, titrations of acids and bases. This is very key. We are going to use this time after time. I think you're even going to do a practical on this, acid and base reactions. Or you should do it at some point of time in your high school years, either grade 11 or 12. But yeah, it's very rare that you're going to finish high school without doing titrations. Yeah, this is very important. So let's take a look and see what is really happening here. The neutralization reaction between an acid and a base can be very useful, as we have talked about previously. If an acidic solution of known concentration is added to a basic solution of unknown concentration until the solution is exactly neutralized, it is possible to calculate the exact concentration of the unknown solution. Right. So that is what titration is all about. We are using the concentration and volume of a known substance to calculate the concentration and volume of the unknown. Right. Titration is a technique where a solution of known concentration is used to determine the concentration of an unknown solution. This process involves the gradual neutralization reaction of an acid by a base or of a base by an acid. Right. So if you're given an acid with known properties, you can find the properties of an unknown base. And then if you're given the properties of a base, then you can find the properties of an acid that are unknown at that point using this reaction. Right. Titration is a method used to determine the concentration of a known substance using another standard solution. So what is a standard solution? A standard solution is a solution of known concentration. Okay. The titration of an acid in a aqueous solution with a base is illustrated in the series of photographs below. Right. The titration of an acid in a aqueous solution with a base. Okay. So let's take a look at this. It is a titration of an acid with a base. Okay, so here in our beaker, we have our acid, right? And then here in our burette, we have our base, right? So we don't know the properties of this acid, right? But we know the properties of a base. So what are we going to do? We keep pouring a bit of base in our acid. Just a bit, right? We have an indicator here in our acid. We have put an indicator inside it. And then when the color of the indicator changes, well, different indicators change color when the reaction has reached an equivalence point. So when the color of the indicator changes, we know that we have stoichiometrically equal number of moles of acid and a base. We know that neutralization has occurred. So because we know the amount of acid that we have poured in, we can then determine the amount of acid that should have been in the beaker to begin with. That is what titration helps us with. Right. So we have an acid of unknown properties, and we keep pouring a small amount of base until the indicator changes color. When the indicator changes color, we know that neutralization has been reached. We are at the end of our reaction now, and using that information we have with regards to the base, we can then determine the properties of an acid. So this is essentially what titration is all about. But which indicator do we use and when do we use it? Because we have a couple of indicators. Let's talk about that. An indicator is used to determine the endpoint of neutralization. Okay, let's go ahead and take a look. We have 3 indicators: methyl orange, bromothiamyl blue, and phenolphthalein. Alright, those are our 3 indicators. So if you're expecting your endpoint, the endpoint of neutralization, to be reached when the pH is between 3 and 4.4, then you use methyl orange. And then if you expect your reaction, the point of neutralization to be reached when the pH is around 7, you use bromothiamyl blue. And then if you expect your pH to be around 8, around 10, when the point of neutralization has been reached, then you use phenolphthalein. So how do you know that the pH at which the endpoint of the neutralization is going to be reached is going to be around 3, and you use methyl orange, around 7 and you use bromothiamyl blue, around 8 and then you use phenolphthalein? How do you know all that? If we have a strong base and a strong acid, then we would expect the pH to be around 7 at the end of our neutralization reaction. In this case, we would then use bromothiamyl blue. And then if we have a weak acid and a strong base, you expect the pH to be greater than 7, around 8, around 9, around 10, even around 11. And then the suitable indicator in this case would be phenolphthalein. And then if you have a strong acid and a weaker base, you expect the pH to be less than 7, right? And then in this case, we would use methyl orange. So there we go. This is how you can have an idea of which indicator you need to use based on the strength of the acid and the base you have at hand. Let's solve some problems.